session, we created a pipeline that processed NGS data, and we created the gene expression table as a result. Focus of today's session will be what to do next with the output we created. We created a TXT file that is actually an expression table, and doing summarization and describing statistical properties of the data is the next essential step in data analysis. Summary statistics and statistical properties might seem like some basic terms, but they're very important. For example, if you conduct a research and write a paper, you want to publish it, results section of your work will always need to contain descriptive statistics part. So we will deal with that part today. On the other hand, descriptive statistics and statistical properties will tell us what are the most appropriate methods for us to use in the further analysis. So we will combine the output that we got from the last session when Elia was running a pipeline to create a gene expression table for the data from the cell line project. We sent you the links to the data sets and also sent you links to download the RStudio in our first two sessions. In case some of you forgot to do this, I will just send these links in chat for everyone. So this is the link data set. I'm just gonna send that in the chat. So this is the link data set on Google Drive. Second link is the link to RStudio. And I will send you another link that leads you directly to the part where you can download the RStudio. So one very important thing when downloading RStudio is that you also need to download R. So you will have an option when you click download RStudio desktop, you will have a sentence and an option to download R because R is necessary to run the RStudio. So in this session, we will be combining T-Bioinfo platform usage, creation of pipelines and output results with the tools like spreadsheet software, for example, Excel, and RStudio to conduct further data analysis. Regarding the spreadsheet software, you can use any spreadsheet software you have on your computer. I assume most of you have Excel, but in case you don't have Excel, you can use any spreadsheet software to have to view the data. We will use spreadsheet software just to review our data set, see how it looks like, what is the composition of the data set, and perhaps do some basic functions in data analysis. More advanced things will be done in RStudio, so please, if you haven't downloaded it already, download it using those links and install it. Just a reminder again, you need to download RStudio desktop on the link I provided, and you will have an option to download R as well, which is necessary to run it. So we created a gene expression table. You can see this green button there, the algorithm we used to create it. And when you open it, it's a TXT file that could be opened in Excel. When you open it, it would look something like this. You don't have to open the data sets we provided just yet. For this moment, let's just review how does a gene expression table look like and what it's composed of. This is a typical gene expression table. It's composed of rows and columns, and these rows and columns contain data for gene expression levels for various samples. On the left side, we have those gene IDs, which start with ENSG and some numbers after that. And on the top, we have sample names, which start with SRR and then a series of numbers. What we have in the central point is actually a matrix of values that represent gene expression levels. As you saw in the last session, there are various types of data. There are FASTA files, FASTQ files, there are sequences, numbers, visual types of data. In this session, we will analyze number or numerical types of data, which contains numbers. So, pipeline that we run on the last session produced a gene expression table that contained values of gene expressions in FPKM, or fragments per kilobase million. That is just a unit. So these are the units of these values that you can see in this gene expression matrix. One very important thing is that table is not composed just of numbers, it also contains the labels. And we will need to differentiate these two. So table is composed of numbers and labels. Numbers and labels together form something that is called a data frame. A matrix is just these rows and columns of numbers that intersect each other vertically and horizontally. So, horizontal lines are columns and vertical lines are rows. When we look at a data set like this, the first thing we can ask ourselves is how to draw some conclusions out of this data. The data set that we created in the last session contained 80,000 genes. Here we have maybe, 25 genes. You can't really view 80,000 genes visually and draw conclusions out of it. You need to summarize it in some way. You need to transform this large amount of values, different values with large variability, to a single value that would describe the whole data set or entire sample, for example. To do this, you need to find central points of the data. They are best used to describe the whole data. How do you find these central points? Well, one way is just to sum all the values and divide them by the number of values, which is a plain average calculation. So average is one of the central points of the data we could use to describe it. You can see that we have some very small values and some very high values like 0.5, and we have values of, 400, 160. We need to summarize them into a single value and average them to get some accurate assessments of how to create some descriptive statistic. Another thing we could do is calculate what is the 50% of our data. What is the point that divides our data into higher 50% and lower 50%? So in essence, we are creating another central value. These two values, means, and the one that I'm speaking right now, central point of the data that divides it in two halves, medians, are called central tendency values. How do we calculate? To show you that, I created a very simple data which consists of just 9 values. Now, some of you are probably introduced to the means and probably to the medians as well, but we will go, as we said, from the very basic things so everyone can follow. Of course, we will later go to more advanced things, and we will be there to take you through each step of the way from transferring from those basic things to the more advanced. Now let's start from the basic things. How to calculate a mean? We have a set of values here, so we just add them up and divide them by the number of values, which is 9, and we will get average. So our mean is 4.5, and that is the central point of the data. On the other hand, I said that the median is another central point that divides it in 2 equal halves. So 50% of the values are higher than the median and 50% of the values are lower. So if you take at this lower part of the image, you can see that 5 is the median. 6, 6, 7, 8 are higher than 5, and 1, 2, 2, 3 are lower. As you can notice, these two values of mean and median, these two results, are very similar, 4.5 and 5. That is a very frequent situation when doing summary statistics, but it doesn't have to be always like that. Sometimes we will have a situation where mean is much, much higher than the median. Let's take an example in this moment. Let's add, for example, imagine that we added 1,000 to that number 11 row. So if I add 1,000 to this, it will be these values plus 1,000 divided by 10. So that would be pretty much, I don't know, 1,000 and something divided by 10. Our mean would be over 100. So just adding a single extremely high value will change my mean from 4.5 to over 100. On the other hand, my median would stay pretty much the same. If I added 1,000 to a calculation of the median, it wouldn't change too much, because medians don't take into account how much higher is the value I added. It is just important that that value is higher than the median, and that is just another value. So my median would probably be 6 in that case, and my mean would be over 100. So means are connected to the number of values, but they're also connected to the intensity of the values, and that's why they're called parametric analysis summary statistics, because they take into account a parameter of intensity. Medians, on the other hand, are non-parametric. They don't take into account the intensity of the value, just the fact that it is lower or higher than the central point or the median. You received 2 versions of the data set we sent you for this session. What we did is we took first 1,000 genes of the entire data set that consists of 80,000 and selected them for this session in order to simplify things and speed up the things as you learn. Later we can use entire data set, but to be more efficient, we just selected 1,000 genes for you to practice. We will use, for example, Excel. We will write functions, how to calculate mean, median, and maybe add mode, for example, which is the most frequent value. So mode is simply the value that repeats the most times in our dataset. Now, to give you some visual perspective of what are these central tendency values, let's review this image. Mean is, as I said, the central point of the data, and as you can see, most of the data is in the proximity of that central point. On this bell-shaped curve, we have a line where you can see that it's written mean, and below that central point, we have the largest portion of the data. What that means is that if I took any random value from my data set, I would have highest probability of finding it close to the mean. That is why we use the mean to describe the data, because it's best used to describe any value of the data with the highest probability. On the other hand, there is another feature of describing the data that I want to introduce at this moment. We found the central points of the data, but we also need to assess the variability of our data. Let me give you another example. I could have a mean of 50, for example, and I don't know, lowest value is 0, highest value is 100, and I have a mean of 50. So my deviation is from 50 to 0 and to 100. But I could also have a data set with lowest value of 45 and the highest value of 55 and still have the mean at 50. So we need to add another feature which describes how much does the data deviate from that center, and to explain the variability within the dataset. One such measure is called standard deviation. As its name says, it describes how much does the data deviate from the mean. So we take into account all deviations of each single values from the mean, and then we create another average out of them, which is called standard deviation. So we combine mean and we combine this variability or deviation assessment called standard deviation, and now we have a more complete picture of how to summarize, for example, a single variable data for a single sample or the whole dataset. When we use medians, we can't combine them with standard deviation for a very simple reason, because standard deviations are used to describe the means. They're actually calculated from the means. They're not calculated from the medians. There is another measure that can be combined to explain the variability of the data when using medians. You can see these numbers and letters here, Q1 and Q3. So you have the median, it's the central point, and you have the Q1 or the lower quartile. What is Q1? If median is 50% of the data, Q1 is 25% of the data, and Q3 is 75% of the data. So we have a certain range from 25% to 75%, and it's called interquartile range. Median is actually between them, and we can combine median plus interquartile range, and we can use it to describe data in another way. There are situations where we will want to use medians and interquartile ranges, and there are other situations when we will want to use, for example, medians and standard deviations, and we'll speak about them later. What is very important when, for example, writing a research paper, you will always use this combination. If you have a data that is appropriate for medians, you will have median and interquartile range in the semicolons, and if you use means, you will have plus minus standard deviation. We'll speak about that later more. Another thing that you can see on this image are the outliers. What are the outliers? Outliers are values that are extremely far away from the median. So they're actually very, very deviant values. Now, if you take this from the statistical perspective, if you asked a statistician what to do with outliers, he would immediately tell you, hey, let's deal with them somehow, let's eliminate them, let's trim them. But in omics data, in genetics, in NGS data, we don't always want to eliminate the outliers, because sometimes that is just a gene that has extremely high expression. It could actually be very interesting for us from the research perspective. They could be something that results from error in measurements, which is exactly the reason why statisticians want to eliminate them very often. But in genomics, it doesn't have to be the case. So we'll also teach you how to differentiate between errors in measurement that produce outliers or just some highly expressed genes that could be very, very interesting for further data analysis. Aside from this, you can see that, for example, medians can be used to compare samples, as is the case with the means. In this case, you can see, for example, that condition 2 has a much higher median than condition 1, which probably means that values of condition 2 are higher across the whole data. Now we will use Excel to run some basic functions on this and create descriptive statistics for the data set we sent you. So briefly after this, I will share my screen, show you how to calculate means, medians, modes, and some other statistics, how to interpret them, and then move to the next step. So, share my screen. A moment, and I will show you how to use Excel this summary. So you will open a folder that contains two data sets, or it's one data set in two different formats. It's called Experience 1000 cell line, and you have it in two versions. You have a TXT version right here, and you have cell version. Please, guys, could you confirm that you can see my screen?
Yeah, we can see it, Dargo, but you are kind of breaking up often. Could you, your voice is kind of, there's some lag out there.
Okay, that's probably with the connection. Okay, thank you. So you have two files. You open the Excel file, and this is what you will see. You will see a data set that is similar to the one we saw before. You have some ENSGs on the left side, and you have SRRs on the top. So these are the labels for our data. These are gene IDs, and these are IDs or labels of the samples. Now you can review the data set. You can scroll down and you can see that it actually has 1,000 genes. You can use your own intuition to draw some initial conclusions. For example, you have some zeros here, you have some lower values, and then when you go down, you will find some extremely high values. For example, here in the we have some values like 4,000, like 1,000, 10,000. Okay, so we have some big differences in the gene expressions, and that is something we can see immediately. But use a statistical approach to summarize our data and draw this conclusion in a more accurate fashion. So I will write median here, and I will write another thing which is called mode here. How do we calculate, for example, let's say mean for sample, which is under the letter H? Just on this box here below the mean, and we type equal average here. So semicolon will open. We just want to select the row of the entire sample by clicking here on age. Quickly, we can see that something is typed here in the formula, which is age, and that is also the way to select entire row. So after we close the semicolon and click enter, our mean, so mean for this entire row or entire sample is 32.8. Said that the unit is FPKM. Units are never in this because they could confuse the software. For example, in this case, we are calculating the mean from numbers. If we added some letters there, that could confuse the software, and they're very rarely typed in these tables. So in this case, we will just remember that our unit is FPKM. We calculated the mean. Let's calculate the median. So we type equal, same thing, semicolon will open, and if we can, for example, we can just write age here and click enter. We calculated the median. It's 8.49. We are already getting some interesting information here. We said that means and medians are both central points of the data, and very often they're similar. We already have a situation where they're quite different, and later we'll see why. Let's calculate the mode. We do the same thing, equal mode. Select this first one, mode month. We do the same thing, age, we close the semicolon and click enter. It will just want to calculate, and we can see that mode is 0. What is mode? Mode is the value that is repeated most times across the sample. So in this case, 0 is the value repeated most times. And when dealing with RNA-seq data, which you will have a lot of zeros. All values, you will have some highly extreme values, and zeros will generally be repeated most times. Decimals, other data, zeros don't have decimals, and they're exactly repeated large number of times, as you can see in every sample. So it's pretty much a conclusion that we calculate the mode for each of the samples, it would be 0. It would vary, but mode would be 0. Now we can see that all three values are quite different, and how do I choose what to use as a descriptive in this case? We have a mean of 32, we have median of 8.4, and we have the mode of 0. First, mode is 0, and it doesn't describe anything. So mode is least appropriate in this case, and we won't speak too much about it in this case. Mean and median are different. We said that medians are very stable. They're not influenced by extremely high gene expressions. On the other hand, means could be influenced by them. So it's clear that we have large number of high expressions that are influencing the mean to increase compared to the median. So when dealing with such data, we will want to use, in this case, median as our best descriptive. And after I run descriptive for all of these samples, I will show you why. Now, we calculated these, but to calculate descriptive statistics for all of them, not just zero. There is a simple way to do that in Excel. So we go here to File, Options, and under this tab here, Analysis Toolpack, we want to make sure that this toolpack is turned on. By default, this will not be in Excel, so you have to turn it on to run the analysis we're going to run right now. After we click OK, Data tab, you will see that here on the right, you have a data analysis button. What do we do next? Let's click data analysis. We will have a large number of functions and analysis we can do. For example, let's choose the one we're interested in right now, which is descriptive statistics. So, okay, and we have this first thing here, which is called input range. That's where we input the range that we input in the semicolons before. Now we just want to select them here. We can do this in a similar way, just by selecting all of the rows. So, summary statistics here, and click OK. Take a look at what happens.
Question on the chat, if you can.
Yes.
There's a question on the chat. Somebody
Okay.
to go back to the
I will just review that.
Data analysis pack in the Excel. If you can revisit that, please.
Okay, I will revisit that. Okay, thank you. So, let's go just a moment to the data analysis. It won't take long. So you go under the file and under the options. Here, where you have these parts, you have the one that is close to the trust center, which is the last one, add-ins. There, you click, and this will show up. You choose Analysis Toolpack and click Go. If you click Go, you will have these 4 buttons. Check the Analysis Toolpack so that it's turned on. So, this may vary, for example, in some older Excel versions. It might not be here at the options, it might be at the settings. But if you have a problem in finding it, let us know after the session and we'll show you how to find it. Okay. So, let's go back to the descriptive statistics. So we go to the analysis, we choose the descriptive statistics and click OK. Under the input range, we select all the rows and click OK. Let's see what happens. This will produce an error, but I want to teach you by producing an error how to avoid it. If you click this, say this one statistics option, choose it, right? We want to choose summary statistics. Click OK. Now it will produce another error. It contains non-numeric data. Why I told you that it's very important to understand that data sets are not composed just of numbers, but also of labels. And if we include the labels in the statistics, it might confuse the program. So our program is at this stage right now, and it can't produce our descriptive statistics because these labels are included. So I click here, labels in the first row. After clicking that, it will start calculating. You can see here at the lower left corner, it says calculating descriptive statistics. Now, for Excel, for 1000 genes, this will take like maybe 15 seconds. There are different types of tools, spreadsheet tools and data analysis tools like R, which have different timings depending on the software and depending on the amount of computing power you have on your computer, and these times could vary. That's why we created this 1000 gene data sets for you, so you can run this in the Excel independent of your configuration. So, done, it will produce another sheet which contains the statistics for all of the samples. You can see the samples up here, and on the right side you have their descriptive statistics. So you have means, you have medians, you have modes, values right here, and you have standard deviations, which we talked about before. This is a very important statistic regarding this data set, and I will explain you why. So, aside from them, we have minimums, which are zeros, as we predicted. node, and we have maximums. Take a look at the maximums. 3,000, 3,500. We have 4,600. So we have some big maximal values. Take a look at this one, 10,000, right? So, which is exactly the name of genes we are dealing with, took you briefly through this descriptive statistics session. So, as I said, median is appropriate for usage in this point. Why? Because standard deviations tell us that our data is very deviant. We have a large amount of those extremely expressed genes, and they're affecting the mean. So mean is much higher than it should be if we didn't have those numbers of extreme values. So in this case, we would use a median. We can see, for example, this median is slightly bigger than this one, and number of genes is a bit highly expressed in the first sample. So we created descriptive statistics for each of the samples. We used formulas to do them in Excel in a very simple manner, but then we created this table with entire descriptive statistics for all the samples. I will go back to the presentation and we actually created our hands-on part with the Excel. So right now I will go to the next slide as a visualization part. So as you can see here, you have some blue values, which are those values that are actually close to zero, and you have some medium values like 100, I don't know, from 7 to 100, 200, and then you have these red values which are extremely high. So this is the same thing that we got from our summary statistics output. Our data is very different. It has different scales, it has different levels. It has some very low levels, and then we have some gaps, and then we have some extremely high levels. Such data is typically produced from RNA-seq output, and it's called non-continuous data. In this session, I will also show you how to convert such data to a continuous type of data. Why would we do that? Well, simple, because our data is better analyzed when using different approaches. We can use the median approach, but sometimes we want to use a mean approach. There are algorithms that use mean, for example, to calculate some statistics for us. Means are dealing with intensity of the value, which is another reason why they're interesting for us, and we will generally want to convert them to the type of the data that has such a distribution that is not like this with big gaps, non-continuous, but rather continuous data. So in brief, I also explained to you the two main types of numerical data. We have non-continuous data, which is typically produced from RNA-seq, and we have a continuous data. I will later show you how does continuous data looks like. Generally, it won't have these big gaps in the data, it won't have big differences, all the data will be condensed and close to each other in values. Now, before we go there, use the RStudio, which I hope most of you installed already. If you haven't installed it or have a problem installing it, you can also let us know directly in the email and we will guide you through that process. Now, I will share my screen again. And we will use, we don't need this anymore, just use RStudio. If you have installed it, you have seen that you needed to install R first, and you install RStudio, which with which is used to conduct data analysis. Why is it different from R, the basic form? Well, RStudio is an integrated development environment for R language, and it is used to improve the workflow of data analysis in R. Open R. You will encounter 4 different sections. So you have this top right section, which is called environment section. You have the file section here, section, and the scripting section, which is marked as United 1 here. These sections has its own functions, and I will take you through all of them during this session. Aside from that, we have, as you can see, many other buttons, toolbars like history, connections, plots, packages, many others, and we will speak about them during the program. Right now, let's use the environment section. What is environment section? It's the section that is used to observe our data frames, objects, see their characteristics, and importantly, import the datasets. Datasets could be imported by writing the code here, but we will use a simpler way to import the dataset from the environment in this moment. You probably had the chance to see this step in the video that we sent. In case you didn't, you can take it now. We go to this button here, import dataset. After clicking it, you select from text. So by default, the first directory that will show up is documents. Go to directory where your data is, data that we sent you, these 2 files, and as we selected from text, we want to select the txt file. Clicking open, this will appear. You have these 2 windows and some options on the left. As you can see here, there are some separators. It says here, data is separated by tabs. So we have a tab delimited file, which is a common thing with txt files. There is another thing here in this window. We have some V's showing up. So this is where my labels should be, but they're not. Some V's are instead of them, and my labels are counted as parts of the matrix. We need to fix this. If we imported this as is, that would be a mistake. It wouldn't be imported correctly. We want our labels to be where these are, and these need to be used as names as well. So to do that, go to heading and select yes. You can see now that my labels are fine. The row names used first. It will also assign names to these labels. So now you can pretty much see that with my data and the labels, data is ready to be imported. Just click import. So 3 things happened here. After I clicked import, in the environment section, this showed up. So this is a data frame that is created. So I can see my data frames here in the environment section. I can see many other things like objects and values, and we'll speak about that later. I can also see that my data frame consisted of 1,000 observations, 1,000 genes, and 11 variables. So you can review the data set. Also see that something happened here in this section. Some code was written as we created this data frame, and it was executed. So console is used to execute the code. Be written here. Thing that happened when I imported the dataset could also be written. And after I click enter, it would execute. Code could be written here, in the scripting section under United 1. We can write the code and then run. also execute here. So both of these sections are used to execute the code, to write the code, but console is used to execute it. There is also another difference. Console is very direct. When you write something there and press enter, it will just run. It doesn't happen in the scripting section. You can write it, you can edit it, run diagnostics, use some tools, run just the parts that you want. You don't have to run everything, and then you just... Okay. The important thing is that under this top left corner, so that our data set, so section is used to write the code and to view the data as well. We have this file section here. We have with 3 periods. After clicking it, let us go through directories. For example, I'm going to go to desktop and select my cell line directory. Example, set this as a working directory here. More set as working directory. As I click that, you can see that code set with D, yes, that file was written. Let's write first line of code here in the scripting section. We will create the summary similar to the one we created in Excel. So we type summary. We can select it here as well. 2 semicolons will appear. We want to type exactly the name of the data frame we created in this semicolon, in between these semicolons. After doing that, we will see that everything matches. And click summary. We will get the summary of all the samples. Similar to Excel, in this case, we also created Q1 and Q3. We have minimums, maximums, medians, means, and Q1 and Q3. We can see the similar situation with maximal values and everything, so I won't repeat that again. Now, to go a step further.
You again, your kind of voice is breaking up terribly. We are not getting the right package. Are you using a microphone, or maybe you can go directly to the computer audio?
No, I'm using directly the microphone of the laptop,
Okay.
the connection or something, but I hope it will be fine now. Okay. So we wrote the first line of the code, summary. Now let's go a step further. For example, we could write something about creating normal data that I spoke about, continuous data, and we can use a function that is called log transformation. In essence, we just do this. We want to create a new object. For example, norm, this sign, and then I'm going to do this very slowly for all of you to understand. Then we are creating this object. You can see that it points to the new object. Now we will use the log function. So we go log, we open semicolon. So we are doing a log transformation of the initial data frame, which is expression genes 1000, and we want to add 1 to this. Why do we add 1? So we don't have infinity values in our data set. We'll speak about that later. I click run. See here that a new created. You can view it now, and you can see the big difference now. Don't have those gaps in the data. Our data is condensed, I don't know, from 1 to 10, for example. Data is very, very continuous. To do this in a summary, let's create another summary of this new frame. Means and medians are now pretty much the same. We equalize them. We can use means, we can use medians now. Data is now normalized. Let's write third. We might want to create, for example, a box plot. Visualize this. We type box plot, open the semicolons, and let's first create a box plot for raw RNA-seq data. So that is the first data frame. with expressions, and here is our output. Here are the box plots. You see the medians are stuck to the floor, and we just have some values. Those are the extreme values that we're seeing. We can't even create a good box plot because our data is not normalized. Our scale is from 0 to 10,000. We can't really use it for interpretation. Now let's create a box plot for new data frame normalized. Run it. That. Our data is on a scale from 0 to 8. You can see that all the box plots are created. It is more continuous, and medians are very similar. Now we can draw some conclusions that each of the samples has a similar median. So we have some small differences between the expressions, and that is another insight for us that we want to narrow down the number of genes, because most of the genes are similarly expressed. We have large number of genes that are, for example, normally expressed in cells, and we will want to narrow down a number of genes to those that are more interesting for us. So we will stop there for now. We imported the data set, we reviewed it, we ran some summary statistics, and we normalized the data by using log function, adding +1 in the semicolons. We used the box plots between normalized and non-normalized data. Normalized data is now ready to be used in most of the statistics and machine learning algorithms. So, in essence, we reviewed summary statistics and we normalized the data in this session. We will continue in the next session, and now I will give you some time to ask questions regarding anything. You may ask questions in the chat, or you may unmute your microphone regarding anything that is of interest for you. Please ask questions. Okay, so I'm just doing first questions. And why are we taking log values? Very simple, because when you do a logarithm of something or use log function, it will return something that is called a natural logarithm, and natural logarithms eliminate these big differences in the data. For example, a logarithm 10 of 1000 is just 3, because 10 multiplied by 10 and another 10 will give you 1000. So we are actually decreasing those gaps. We're equalizing our data. We're putting it on a more equalized scale. Pratim has written you 4 codes that we used here. One is for summary. Another one is to normalize the data. On this second one, you can use it in this form. It will produce some infinity values, but as you can see here, you add 1, those infinity values will disappear. You have the box plots, and you can use the box plots to review visually the difference between normalized and non-normalized data. I show you another function here. It's called histogram. Now, histogram is used also to analyze distribution of the data. For example, let's create a histogram of this normalized. If we type this, we will produce an error because it says numeric. Now, that's because, as I told you, labels could confuse the software. So we must distinguish labels from numbers. We must transform our data frame into something that is called a matrix. Let's do this. So we'll create, for example, age 1 object. Matrix here. Normalized expression. So we created another object, Stage 1 is now a matrix. Use the hist function. 1 use a histogram. It's another tool for visualization. We will use this in the next section more. Now I just showed you that we can use other visualization tools as well. Okay, let me review this. Any other questions? Okay, so Vamshi is asking, can we explain briefly about the box plots and the outliers? Okay, so I will go back to the presentation and this to you. So here are the box plots. Okay, so each box plot consisted of several values. We have minimal values, maximal values. What is important for us are the medians, which are on these box plots present these lines folded, and median divides the data in two equal halves. We have 75% of the data and 25% of the data. So we have 25% of the data that is lower than the median and 25% of the data that is higher than the median. And they are called interquartile range when we calculate the range between them. So that's what the box plot represents. It represents minimums, maximums, medians, and interquartile range. Ask about outliers. Outliers are values that are extremely far away. For example, this one is on the bottom. It's very, very far away from the median. Outliers can be in measurement, and they're eliminated very frequently, but sometimes they could be just highly expressed genes. For example, this one could be highly expressed genes, and we wouldn't want to eliminate. Okay, so other questions?
Hello.
Oh,
Hello.
hello, I can hear
Hello.
you.
Yes, yes. It's me, Vamshi.
Okay.
I'm just asking about the box plot that you have created about the example right there for the cell lines. Now you have created right in the
Okay,
RStudio.
so what do you want to know about the box plots?
I mean about the example that you have shown about the cell lines. So can you explain about the cell lines on the box plot, please? Can you open the
Okay.
RStudio? You.
Yeah. I'll share my screen again. I will explain this to you. So,
Yes. Yes.
thing we can see here in the plot section, I can go back, right?
Yes.
I can view all the plots that I have made.
The normal expression.
Yes, I will for this one, I will increase the value of this one, for example, 2,000, 1,000, and I will increase this image for you to see. So you have the box plot, normalized data. You remember the step where we did the normalization, where we eliminated those big gaps in the data and created continuous data. So now we have the box plot explain everything from that continuous data. You have the samples here. Oh,
Yes.
and of the samples you have median gene expression, the entire sample, in the entire sample of those 1,000 genes. So median is 2. They're all close to 2, as you can see. There are some small differences. You can see some very small differences. But in this case, we normalize the data, and we can use these small differences to make conclusions. Small difference is important. It means, for example, that 50 genes are highly expressed in this one and they're not expressed in this one. So we have the outliers right here. The box plot function calculated them as outliers, something that is extremely highly expressed. But when we use gene expression data, we don't want to consider them as something that is of measurement. if the outlier was here below, we would be able to consider it as something that is just a noise. But since it's highly expressed, it could be interesting for us. So it's impossible to have errors in all of these measurements. That is another thing we can summarize here. So some of these genes could be interesting for us, even though they're outliers. Is there anything else that is interesting to you to ask? Before you ask, I will also explain another thing. The first data frame we created was from raw RNA-seq data, and we said that units were FPKM.
Yes.
But when we normalize the data, units are no longer FPKM. This is unitless data now.
Yes, yes.
Because we adjusted the entire scale. We don't have units anymore, so we just have numbers. But these numbers are absolutely enough for us to use them in the machine learning algorithms, in data science analysis, and other things. You will see that pretty much, even if we have different types of data, Elia explained you on the previous section, we have sequence data, we have FASTA files, we have FASTQ files, gene expressions, we even have the visual data like images. But generally, even images or pixels are all converted to numerical data in the end, and numerical data is most optimized to be used in data analysis.
Okay, so what do we conclude from these box plots from here, 1,000 genes?
Okay, we can conclude three things. There are small differences between gene expressions. So differences are present, but they're very small. And for that reason, we will want to narrow down the number of genes we're analyzing, and we will use machine learning algorithms for that in the rest of the program. We want to narrow down number of interesting genes. We want to eliminate most of the genes that are normally or similarly expressed. So that is the first insight. We want to narrow down on some interesting genes.
So we can
On the
consider
other
the
hand,
outliers also.
yes. On the other hand, we have some differences. They're not identical.
Yes.
As of the outliers, the conclusion is that these outliers are not errors in measurement, but could be some very interesting genes. In my opinion, we could analyze just these outliers, and we will probably come up with some interesting results regarding these breast cancer cell lines. So, we have 11 different breast cancer cell lines. Most of their expression is similar, but there are some differences. In each of the samples, we have some extremely highly expressed genes for each of the breast cancer cell lines. So those would be some conclusions in brief, but there is another conclusion which we can see from the box plots from the Q1, Q3, and the median, that our data is now continuous. I will show you how a non-continuous data looks like. It looks like this. All the medians are stuck to the bottom to create the box plot. So this is RNA-seq data, this is normalized data, and we also created a histogram to show you how normalized data looks like on the histogram. There is another conclusion that large amount of data here is close to zero. So we will want to deal with that, but we will do that in the next session.
Thanks so much, Dr.
So the next session, we will use exploratory data visualization to create these visualizations like histograms and box plots, but create many others, like, for example, heat maps, and combine them with correlations and statistical significance to do exploratory data analysis and visualization. Any more questions? Okay. And see you in the next session. Thank you, Soha. Okay. Thank you very much, Sarah.